So we're going to get started with solving this truss. And so the first thing that we're going to do is that we're going to go ahead and solve for all of the angles in the members, right? Okay, so we can do this a couple ways. The way that we're going to start is we're going to solve for the angles in the members. Okay, so how we're going to do this, we're going to start to divide up the truss so that we have these 90-degree triangles, right? So we have, this is 3, this is 2, this is 2, okay. This is also 3. Okay, and then this is 3, this is 2. So you notice that we're using the distances to find the angles, right? Okay, so, and we remember that, so mainly to solve a lot of these problems, we're going to go ahead and use our trigonometry functions. Okay, so we have tangent is opposite over adjacent, right? Okay, so to find the angle, theta is going to be inverse tangent. So this is the tangent of theta, right? So inverse tangent of opposite over adjacent. Okay. So essentially, we turn the tangent back into theta by applying inverse tangent to it. All right. Okay. So let's go ahead and solve for these angles. So we have the angle here at A is going to be opposite over adjacent, right? So adjacent is 3, so this is inverse tangent of 3 over 3, okay? This angle is going to be inverse tangent of 3 over 3, okay? This angle is going to be inverse tangent of 3 over 2. Okay, this angle is going to be inverse tangent this angle is going to be inverse tangent. Okay, so we have opposite over adjacent, right, of 2 over 2, okay? And I get that we can just go to 90 degrees and subtract, okay? But just for demonstration purposes here. So we have, this is going to be inverse tangent of opposite over adjacent, right, of 2 over 3, okay? And at that point, we basically have all of the angles, right? And then this right side is kind of a flip, right? Okay, so all the distances are equivalent on the right-hand side. All right, so essentially once we find these angles, we have all the angles for the right-hand side. Okay, so let's start to take a look at these. Okay, so we have, and I'm actually going to record them somewhere else. Okay, so I'm going to go ahead and fold this paper in half just so we see half of it. All right, and we're going to start to record the angles. Okay. So we have angle BAD is going to equal, I'm going to go into my calculator here. Okay, so we have 45 degrees. Okay, as soon as I know that BAD is 45 degrees, I know that, so basically this is 45 degrees, right? Okay, I know that this angle up here is 45 degrees. Okay, and then we know that this angle here is going to be inverse tangent of 2/3. So that's 33.69. Okay, And we're going to call this point right here. So the points that we've used to this point are up to A, B, C, D, and E. So we're just going to go ahead and call this point F down here. F's going to be too confusing. We're going to call it G. Okay, so we basically have the angle GDA is going to be 45 degrees. We have the angle BDG. I did this backwards. We're going to call this ADG. Okay, just to keep organized. So ADG is going to be 45 degrees. BDG is going to be 33.69 degrees. And then we have inverse tangent of 3 over 2. Which is 56.3 degrees. Okay, so we're going to call that DBG. Okay, 56.3 degrees. And then we have the inverse tangent of 2 over 2, which is inverse tangent of 1, right? So we have BDE is equal to 45 degrees. Okay, so at that point, we basically have all of the angles in our drawing here. Okay, where am I wrong? BDE? Yeah. Oh, you're completely right. It's 4, right? 4 over... Oh, it's 2 over 3. I apologize. 3 over 2. Sorry about that. Okay, it's 56.3. Is that correct? Okay, awesome. Okay, BDE is 56.3. You guys are so smart. Okay, 56.3. Okay, so that is, so then we can go ahead and we can basically flip over all the rest of the angles. Okay. Okay, our last one here is just angle DBE. So that's going to be 180 minus 56.3 minus 56.3. And I'm sure I'm wrong, and I'm sure I should know that already. It's going to be 67.4. Okay, so at this point we have all of our angles figured out. So I'm just going to go ahead and keep recording them. 67.4 degrees. Okay, so now what we're going to do is we're going to go ahead and figure out the moments. Okay, so we know that our equation for moments has to be, the sum of moving around on me here. Okay, so we know that the sum of the moments about A has to be equal to 0. Okay, so we start to go ahead and add up the moments, all right? And our idea here is that we know that because we have a roller connection, we know that we have a RCY force. We know that we have an R, and we're just naming that the reaction force at A on the y-axis, so RAY. And we have RAX. Okay, so we have those 3 forces, right? Okay, so now there's no moment at RAY because the distance from A, the point of rotation, is 0, right? So there is a moment at RCY. Okay, so all we're going to do to sum the moments is we're going to take our forces. So we have 1,000, 250, 500, and we have RCY. Okay. Now all of the 1,000, 250, and 500 are all negative. RCY is going to be positive, right? Okay, so let's go ahead and record those. Okay, so we have the force at D is going to be negative 1,000. Force at B is going to be negative 250. Force at E is going to be negative 500. Then we have RCY, we have RAY, and we have RAX. Okay, so essentially what we're solving for is this RCY, RAY, and RAX. All right? Okay, now to get RCY, we're going to solve for the moments, right? So we're going to sum the moments. So we have sum of moments about A is going to be 1,000, I'm sorry, negative 1,000 times 3 plus negative 250 times 5 plus negative 500 times 7 plus RCY times 10. Okay, so we go ahead and we calculate that out. So we have 3,000 plus, sorry, negative 3,000 plus negative, whoops, 1,125, or sorry, it's 1,250. Plus 500 times 7 plus 3,500, negative 3,500. Okay, so we're going to go ahead, negative 3,000 plus negative 1,250 plus negative 3,500 plus RCY times 10. So what we're going to get is, and this is all going to be equal to 0, right? Okay, so what we're going to get is we're going to get we get 775, or sorry, 7,750 divided by 10 equals RCY. So, and that's going to be 775 equals RCY. Okay, so that's the summing of our moments, right? So we get RCY is 775. Okay, so now what we're going to do is we're going to sum the external forces, right? So this is fairly straightforward. Okay, so we have our negative 1,000, negative 250, negative 500, and then we have RCY, which is positive 750, plus RAY is going to result in 0, right? So they all sum to 0. Okay, so let's go ahead and do that. Okay, sum of force in the y direction is equal to 0, so that's going to be 0 equals, and then we have negative 1,000 plus negative 250 plus negative 500 plus 775 plus RAY, and what we get, let me do my calculations. Did I make a mistake? Yes, yep. Okay, so what we get is 975 equals RAY. Okay. So we get 975 equals RAY. All right, and RAX is going to be 0. Okay, RAX is 0 because there are no other forces. It has to sum to 0, therefore it's 0. Okay, so now we're going to go ahead and do our free body diagrams, right? So we have our external forces solved, and now we're going to go into going kind of point by point. All right, now you can either do this by making separate diagrams of each point. After much experimentation, doing the diagrams in place is probably easier, okay? So let's go ahead and start drawing that out. Okay, so we have our values here. Okay, so we're going to go ahead and so we are now at the point where we have we've done our external forces. So essentially what we have here is we've figured out all of the angles based upon our distances, based upon the length of each member, right? We've used inverse tangent to find all the angles. Then we summed all the moments to 0. Okay, so that's how we got RCY is equal to 775. And then we summed all the external forces to 0, and that's how we got RAY is equal to 975. Okay, and then we have RAX, which is 0. All right, so we went ahead and went from this main, this is just the original kind of diagram of the drawing of the truss, and now we've gone ahead and we've created this this document here. Okay, so basically what we have here is that we have our list of angles and our known forces. All right, now this is just kind of for us to kind of record everything that we know just kind of in a list fashion. And then we also have this main drawing. So this is going to be the drawing that we come back to, okay? So what I have here is that I have all of the angles and all of the forces in one drawing around each point. Okay, or each joint. Okay, so basically we have A, B, C, D, and E. I've labeled all the everything I need basically to draw a free body diagram of each individual point. All right, so we're going to go ahead and start with A, and what we're going to do is we're going to go ahead and make a separate diagram of A. Okay, so we're going to go on a separate piece of paper here, and we're basically going to copy over a free body diagram of A just to make it easier to work with. Okay, so we got A. Okay, so we have, oops, see, I already made a mistake there. All right, so we got A. We have FAD, right? Okay, and we have FAB, and we have RAY, and we have RAX. Okay, so those are our forces acting upon point A. All right, now the thing that we're going to assume here, and what makes these equations kind of difficult, is we're assuming that these are in tension. Okay, so notice I'm using a pencil to put this in. Okay, so we're assuming that these are in tension, right? Okay, so and what tension means is that the force is pulling into the center of the member. Okay, so this is, we're assuming by putting this arrow here, we're assuming that this FAD is in tension. It means that it's pulling into the center of the member. All right. And that has ramifications for how we're going to set up our equations. Okay, so that's our assumption there. All right, now we go back. We know that RAY, actually we don't, and we know this is 45 degrees. Okay, so now let's look at how we're going to solve. So basically our strategy here is that we're going to sum the X and Y forces, right? So our two equations here are, we're going to sum the forces in the X direction, which are going to be equal to 0, and we're going to sum the forces in the Y direction, which are also going to be equal to 0. Okay, so we're looking to set up equations that use this formula, summing the X's and summing the Y to 0. We're looking to come up with equations that allow us to solve for our unknowns, which are FAD and FAB. So that's our overall strategy here. All right. Now to do that, we're going to use the trigonometry functions, right? And here's how we're going to use them. All right, so we're going to take sine 45 as an example. So sine of 45 the sine of 45, sine of theta, in this case it's 45 degrees, right, is equal to the opposite side over the, over hypotenuse, okay? So that's the idea, okay? So sine, we can replace sine with the opposite over hypotenuse, all right? Now, so if I wanted to solve for FAD, okay, FAD is our hypotenuse. So one thing I could do if I wanted to solve for our hypotenuse is I could multiply the hypotenuse by, I'm sorry, if I wanted to solve for the opposite side, I could multiply the hypotenuse by opposite over hypotenuse, and it would give us the opposite side, right? Okay? All right. So in terms of our equation, that would be that the opposite side, so if I take this right here, okay, and I take this is our opposite side. In our case, in our equation here, I'm going to go ahead and erase my arrowheads. Oh my gosh. You gotta be kidding me. It's a horrible erasing. It is the world's oldest pencil. You have to be kidding me. Okay, so this is why I don't like paper and pencil. Okay, so so basically what we have here is we've got this. So this is our. If we go ahead and we draw our x component, or sorry, our y component here. Actually, we're going to draw it out here. Let me further horribly erase this. What is up with that? Oh, thanks, pal. That's really nice of you. I appreciate that. I can't tell you how much I appreciate that. Okay, so we have a much better eraser here. Okay, thank you. Don't get your eyes stabbed out. You ready? Okay, thank you. All right. Okay, so we got we have our we're going to go ahead and draw our y component of FAD up here. Okay, so we're going to go ahead and dot it up. Okay, and this is going to be our FAY. Okay. Now remember that we're assuming that FAD is in tension. That means it's going up and to the right. So that means we're assuming that our FADY is going in this direction, is up, and our FADX is to the right. Okay, that's our assumption here. All right. So this is our FADY, and this is our FADX. All right. So let's take a quick look at that. Okay, so this is our assumption here. All right, so we have FADY, FADX. All right, and just because it's going to make life easier on us, we know that because of alternate interior angles that this is going to be 45 degrees also. Okay. All right, so we go ahead and we draw that external triangle. We draw kind of these imaginary lines. We're dividing up the forces, right? Okay. All right, so let's get back to our equation here. Okay, so we have our triangle there, so we know that in this case our opposite side is FADY. Okay, so this is FADY. All right, we know our hypotenuse is, okay, so we know that sine is equal to opposite over hypotenuse, so we can put in here, we can replace opposite over hypotenuse with sine theta. Okay, in this case it's 45 degrees, right? Okay, so sine of 45 degrees. And we know our hypotenuse is FAD. Okay, so that is the equation we're going to use. So if we want to know FADY, we can write it in terms of FAD, which is actually the thing that is our unknown. That's what we really want to figure out. Okay, so we can do FAD times sine of 45 degrees to replace FADY. Okay, and we can do the same thing with cosine. All right, so we have cosine of theta is equal to adjacent over hypotenuse, right? So adjacent over hypotenuse. we can multiply the hypotenuse by adjacent over hypotenuse and get adjacent. Okay? So in terms of our equation, the adjacent side is FADX. Our A over H is cosine of 45 degrees. Okay, and our hypotenuse is FAB. Okay? So if we're looking, if these are our two unknowns, right, FAD and FAB are really what we're trying to figure out here. Okay? That would allow us to, basically that's what we're trying to solve for. We're trying to solve for all the internal forces on the truss, right? So we've written our FADY and our FADX in terms of FAD and FAB. Oh, I'm sorry, I was wrong. I apologize. This is FAD is our hypotenuse, not FAB. Okay, so we've written FADY and FADX in terms of FAD. Okay, I apologize. On this cosine, it's FAD, not FAB. Okay? All right. Okay, so let's go ahead and write our first equation. So we're going to start with the sum of the forces in the y direction. Okay, so we're going to say the summation of the force in the y direction. So we have two forces in the y direction, right? We have RAY and FADY. Okay? Equals 0, which equals RAY plus FADY. Okay. So what we end up with here is we end up with RAY is 975. Okay, so we get 0 equals 975 plus, and then FADY, we're going to replace that with FAD times sine 45. Okay? Sorry, and this was a separating line here. Okay, so we get FAD times sine 45. Okay, so now this lets us use this sum of the y forces to solve for FAD, right? Okay, so we go ahead, we do a little bit of algebra, right? We add negative 975 to both sides. And we divide by sine of 45 degrees. That's going to give us FAD. Okay, so we go ahead and do the math, which I am going to do as quickly as possible here. Okay, and that's going to give us negative 1,378.86. Okay, so negative 1378.86 equals FAD. Okay, so now is when our forces change here. So we got a negative, which means that FAD is not going, it is not in compression, or I'm sorry, it's not in tension. Okay, now we assume it's in tension to this point. But when we get a negative value for FAD, we now know that it is not in tension. We know that it's in compression. So that's like a major part of this here. So we go ahead, we go ahead and we change the direction of the arrows. Okay? We know that FAD is equal to 1378.86. Okay, and that's negative. However, what I'd like you to do is, instead of notating it as negative, we want to just put a C after it, that it's in compression. Okay? And then we're going to go ahead and we're going to update our original diagram. Okay? So essentially what we have here is we have, in our original diagram now, we have 1378. So FAD is 13 1378.86. Okay, and that's in compression. So we're going to change the direction of our arrows. Okay, so remember our arrows have to be in opposite, right? So we're going to go ahead and put our arrows pointing the other way. Okay, so now we know that this is 1378.86, and the direction of the arrows shows us that it's in compression. Okay, and that's going to affect the way that this vector is used in future calculations. Okay, so that's how we know. It just flipped from tension to compression. All right, that's a real sticking point with starting out on these problems. Okay, because it's negative. Okay, and it's in compression, right? We can put a C after it to say that it's in compression. Okay. So we're going to go on with our problem here. So we have, so we're still working on the A vector, right? We're back to our calculation, and we're going to go ahead and start to sum the X forces. Okay, so we're going to go ahead and start to sum the X forces. So for the X forces, we have FADX, right? That's one of our X forces. So when we sum the X forces, we're going to restate our theorem formula. I always am fuzzy on those words. Okay, so we're going to sum the f of x is going to be equal to 0, right? So that means that 0 equals, and then we're going to get all of our x forces. So we got RAX plus FAB plus, and then FADX is going to be our other x force, right? So the x component of FADX. Okay? All right, so we're summing those forces. So now we're going to start to substitute in. All right? So we have 0 equals RAX is 0, FAB is our unknown. And then FADX, remember that we're going to take FADX and we're going to substitute in FAD times cosine of 45 degrees. Okay? Okay, now, in this case, because we know it's compression, we know that FAD is acting down and to the right. Okay, so in addition to these, so now that we know it's down and to the right, we know that these vectors are actually different, right? So originally we wrote FADY as pointing up. Okay, we now know that FADY is pointing down. Okay, we also know that FADX is pointing to the left, not the right. Okay, so notice how that changes, right? So as soon as we got that negative value for FAD, now the component vectors are also in a different direction, right? So now FADX is to the left, FADY is down, all right? So we know that FADX is going to be negative. Okay, so we can go ahead and put in that negative value for FAD. Okay, we know that the result, FADX, needs to be negative, so we go ahead and use the negative value for FAD. Okay, so we got negative 1378.86, and we're going to multiply that by the cosine of 45 degrees. Okay, so we go ahead and do our math, right? So basically what we have here is we have FAB equals, now remember that basically I'm adding 1378.86 times cosine of 45 to the other side, and then I'm just flipping it about the equal sign. So it ends up that FAB is 1378.86 times cosine of 45 degrees. Okay, so we're going to go ahead and do the math on that. Okay, and we get exactly 975. That checks out, right? So basically we have FAB equals 975. Now that's exactly as we would have expected, right? Because 45 degrees means this is an equilateral triangle. So if we were just solving for the two sides, we would expect that that ADY and FADY and FADX would be identical. Okay. All right. So in fact, FAB ends up being 975. Okay. So we're going to go ahead back and we're going to update our original diagram. Okay. So FAB stays in tension. FAB was positive. So we go ahead and update FAB as 975. All right. Okay, that stays in tension. And we can also update our list of variables. So now we have FAD equals 1378.86 in compression. FAB equals 975 in tension. Okay, also if you wanted to write down, now you could, if you wanted to, not write this down, we could go back to it. It might be helpful for you to write down what FABX and FADY and FADX is equal to as well, if you wanted to, just because it's going to help you out on the next one, which is D. Okay? All right, so we could write down FADX is equal to $975, and FADY is also equal to 975. These are also in compression. Okay. All right. Okay, so that is kind of where we're at this point. So we've solved FAD, we've solved FAB. Okay, so now we have 1, 2, 3, 4, 5 unknowns yet to go. All right. Okay, so our next one that we can solve for, if you look at the this one was incomplete, so we had FCY. FCY was 775. Okay, so the next thing that we can do kind of either one of them. We can either do we can either start with FCY, or we can start at point C, or we can do point D. Okay, for the purpose of the demonstration here, we're going to go, okay, just because it's more complicated. All right, so we're going to go ahead and just like we did on A, we're going to go ahead and do it for D. Okay, so we're going to go ahead and switch. We're going to get a new sheet of paper, right, because these take a lot of space. All right, so we're going to go ahead and draw the diagram for D. Okay, so we have D. We essentially have we have three forces here. Okay, so this is FAD. Okay, and remember, oops, I accidentally drew this in the wrong direction. So remember, FAD is in compression. Okay, so remember that if it's a known value, if we know it's in compression, it's in compression. If we don't know yet, it's in tension. Okay, so we assume it's in tension unless we know that it's in compression. All right, so we have 1378.86 in compression. All right. So now we're going to do the exact same thing here. We're going to go ahead and we're not going to go back through all the trigonometry stuff that we did on the last version. So we're just going to go right in with kind of labeling our stuff. So we have negative 1,000. These are all in foot-pounds, so we don't really need to label that. Okay, and then we have FDB. And we have FDE. Okay, a couple things we also know. So remember, so this vector FAD is pushing up, right? So the direction of this vector is pushing up. So when you start to draw your component vectors, right? So we know that FADX is going up. We know that FADY is going up. We know that FADX is going to the left, right? We know that FADX is 975. Or sorry, FADY is 975. We know FADX is 975. Okay. Also, I'm going to go ahead and put in my my angle measurements, right, because we're going to need those. 33.65. Okay, so we got 33.65. We got 56.3 degrees. Okay, so we have those are our component vectors with the 45 degrees, right? Okay, so now we're going to go ahead, and this is where we're going to start to set up our summations. Okay, so we have our summation. Our summations. Okay, so we have a summation of f of x, not f of x, of our forces in the x direction. We have our summation of forces in the y direction. Okay, so our summations of forces in the x direction are going to be, this is FADX, right? So we have FADX plus FDE plus, and then we have FDBX. Okay, so FDBX is another one, right? Okay, thank you guys so much for hanging in there. I know it's a long time to take notes. These problems last for a long time. So we're actually, after this point, we're actually going to take a break. Okay, so just hang in there. All right. Okay, I'm just going to continue on. Just hang in there just 1 second. Okay. All right. So So with our y values now. Okay. So with our y values now, we're going to go ahead and look at the y components, right? So we have FADY. We have our f of our force at D, which is 1,000, right? Which is negative 1,000. Okay. We have the y component of FDB, right? So we have FDBY, okay, which we assume is negative, right, because it's in tension. Okay, so this FDB is our next one, right? So FDB is going to be, we assume that we have a force FDBX, which I'm just going to draw it kind of above here. All right, so we have our FDBX, okay, and then we have our FDBY, right? Okay, and that the theta there is 56.3 degrees for FDBY. Okay, so just to take a quick look at that. Okay, so drawing this gets a little bit confusing, right? So I just kind of draw it just right above so I can keep it kind of in place. There's probably a better way to do it, but that's just how I can do it right. Okay, so I know that this FDBX goes straight on this FDE, but it'd be very difficult to see, so I just draw it slightly above it. Okay, probably not the best way to do it, but that's what works for me. All right, so we're continuing with our summation here. Okay, so let's go ahead and calculate in here. So remember that we can. So we're going to start with our summation of y. We know this. We know this sum. Both of these sum to 0. So we're going to start off with our y. We're going to have 0 equals FADY. We already know that's going to be 975. We have negative 1,000. And then we have, because we're assuming that FDBY is in tension, we're going to call that, so this is the sign, just remember it's the opposite over hypotenuse, that's how you remember which one to use. So we're going to call it FDB times the sine of theta, which in this case is 56.3 degrees. Okay? And that's going to be negative. All right? So that is basically the gist of this here. So we're going to go ahead and start to simplify. So we end up with 25. We get negative 25 on this side, divided by sine of 56.3 degrees. equals negative FdB. Okay, so obviously the negatives are going to cancel out, so we get 25 divided by the sine of 56.3. Okay, so we end up with 30.05. Okay. Okay, so for FDB, we end up with 30.05. Okay, so now we're going to go ahead and we're going to substitute back in. So this ends up being positive, right? So we get a positive value. So in this case, because we get a positive value, right, so if FDB is a positive value in this case, we're going to say that it is in tension, right? So it stays in tension. Okay, so this does not change right here. All right, so this is in tension. We end up with 30. Okay, 30.05. I take that back. I made a mistake there. Okay, that is going to be in compression because that means that the FDB is positive, which means that no. Okay, because it's positive, it is in tension. I apologize. Okay, so we end up with 30.5. So we're going to go ahead and substitute back in. Okay, so we have our summation of Fx, of the x forces. So we have FADX. So FADX is going to be 975. It's going to be negative 975 because it's to the left. Oh, I'm sorry, it's going to be 975 because it's to the right. I apologize. And then we have FDE. So we're going to add on that FDE. And then we're going to add on to that FDBX. Okay, so the X component of FDB. Okay, so how we're going to get FDBX is that we're going to take FDB multiplied by the cosine of theta, which in this case is 56.3. All right. Okay, so when we go ahead and solve that out, it's going to be 0 equals 975 plus FDE plus FDB times cosine, so that's going to be 30.05 times the cosine of 56.3. Let's go ahead and do that math. Okay, we end up with 975 plus FDE plus 16.67. Okay, so we go ahead and add those up. Okay, so we end up with negative 991.67 equals FDE. Okay. All right, so we go ahead and we're going to transfer that value back onto our original diagram. So because FDE was negative, turned out to be negative, we know that it's not in tension, it's in compression. Okay, so 997.67 in compression. Okay, so we're going to go ahead and pause there. We're working on point D here. Okay, so remember that we went on to point D, and we actually made a mistake. By we, I mean me. Made a mistake here, and that was that as I was doing the calculations for D, basically this negative 25 degrees here. So when I added this should have been negative. When I brought it over to the other side, it should have been positive, okay, resulting in a negative value for FDB. Okay, because FDB was negative, which would have been negative 30, it puts FDB into compression. Okay, so I went ahead and made the correction here. So FDB is going to be in compression. We want to take a look right here. So remember, we're correcting our work. That was my mistake. So FDB is going to be in compression, so the 30 is going to be in compression. Okay, so that obviously would cascade then through our other calculations. Okay, so our main thing here is that if 30 is in compression, so if FDB is in compression, then it's going up and to the left now. Okay, so it flipped as well. So it's going up and to the left. So that basically says that now this is not pointing down, right? Okay, it's actually going up. So our y calculation, the y is going up, and the x is going over to the left. Okay? All right, so our component vectors flip also, right? Okay, so now what we're going to do is we have to go back and look at our summation of the x forces for D. Okay? So basically when I brought 30 in here, that 30, because you can see that FDX is going in the left direction, that should have been negative, okay, which made 16 negative, which is fine. Okay, so when I added those together, I should have had 975 plus a negative 16.67. That would have given us a value of negative 958.33 is equal to FDE. Okay, all right, and that was mainly that's our correction. Okay, so we take a look at then we brought those values back over. Okay, we brought our values back over, and essentially we have 958.33. Okay, in compression. All right, so we have kind of half our vector or half our truss solved here. So now we could go ahead and move on. So because on E here, it would be difficult for us to solve E at this point, right? Because we'd have a case where our y vectors, we'd have two unknowns for the y vectors. We also would have two unknowns for the x vector. So it's really not possible for us to move over to E. Okay. For B, in the same way, we could actually move down to B because we would only have one unknown in the y direction, but that's going to be an awful lot of calculation. So for me, it's a lot easier to move over to C and solve C at this point. Okay, so we're going to go ahead and solve for C. All right, so we got C. We're going to go ahead and do our free body diagram for C. So we're going to go ahead and draw it. Okay, so we got C right here. We have two forces, right? We're assuming that they are in tension. Okay, and that is FEC, and we have FBC. Okay, those are our two forces that we're going to be solving for. We also have FCY, and that's going to be 775. And our angle here is 45 degrees. Okay, So that is our angle. Okay, so we're just going to go ahead and sum the forces again. All right, now for this one, we want to go ahead and obviously the x values that we're going to need here, the component values, we're just going to draw straight up from the point C here, and we're going to have FECX and FECY. That's going to be our x and y components of FEC. All right, and this is going to go really very directly along the lines of how we solve for A. Okay, so let's go ahead and set up our equations. Okay, so we're going to solve our equations, and we're going to go ahead and sum. We're going to sum our x values, right, are going to sum to, so all of our x components, really we only have two x components, right? We have FBC and we have FECX, and then the sum of our y components, we have FCY, we have an FECY. Okay. All right. So those are our only loads coming off, or our only forces in this equation. Okay. So we know already. So basically, we could really start at either place here. Okay. I'm sorry. We can't start at either place. So we have FCY we already know, and FECY is our unknown, right? So so our unknown FEC, we're gonna use that in our summation of the y forces. These are going to be 0, so we set them equal to 0. We have FCY is 775, that's positive. And remember, we're going to get the y value here. So remember that this is also 45 degrees. Okay, so it's going to be the sine, right? So this if our okay, so remember our alternate interior angles. So this equation here, or this angle here, is going to be 45 degrees, just like this is 45 degrees. So this is our opposite side. So when we start to do sine or our trigonometry, our FEC is going to be in terms of sine again, because it's opposite over hypotenuse, right? Okay. Make sure this is in focus here. All right. So we're gonna state it in terms of sine. So we have FEC times the sine of 45 degrees. That's going to give us negative 775 over the sine of 45 degrees. It's going to be equal to FEC. Okay, so we're going to do the math on that kind of quickly as possible here. So we got 775 divided by, or negative 775 divided by the sine of 45 degrees. That's going to give us 1096. So it's going to be a negative 1096 equals FEC. Okay, so remember that puts us right. Okay, so we got the negative value. We're going to FEC is now in compression. All right, so basically that makes these values turn the opposite direction, right? So if FEC is pointing in this direction, we know that the x portion, so FECX has to be going right, not left, and FECY has to be going down, or sorry, down, not up, right? Because we have to get to that same point. So with vector addition, if this vector is ending up right here, and we're doing this head-to-tail addition, we know that FEC is going to the right, FECX is going to the right, FECY is going down. Okay, so now we can go do our summation of our x forces. Okay, and that's going to be FBC. Okay, now we know that FBC is going to be negative, right? Because FBC is, we assume that it's in tension. That means it's going to the left. Okay, so we have a negative value there. So we have negative FBC, whatever that is. Okay, and then we're adding that to And then this is going to be the cosine of FEC. Okay, so we're going to use our cosine in this case because we're doing the adjacent angle, right? And we know that's going to be positive. So FEC times the cosine of 45 degrees. Okay, so we're going to end up, and we know what FEC is, right? We know it's negative 1096. Okay, so we're going to end up with FBC equals the cosine of FEC, right? Of 1096 times the cosine of 45. Oh, my mistake. FBC divided by the cosine of 45 degrees is going to equal FEC. Oh, I made another mistake, guys. Sorry about that. I should have substituted all the way in here. So we got FBC is going to equal, and then we know FEC, right? So FEC is going to be 1096 times the cosine of 45 degrees. Okay, there we go. Okay, and so we get 774. .98. Okay, so we get negative 77.4 times 0.8. Now, the thing here is that because it's negative, right, it's pointing to the left, so we actually know that this is in tension, right? Okay, so even where we got a negative value here, we can see that because it's pointing to the left, whoops. Okay, I apologize. Because this value FEC, the x part FEC x, we know it's going to be positive. This 1096 should have been positive, resulting in a positive value for FBC. Okay, so FBC is positive. That means that it's going to be in tension, remain in tension. I apologize. Okay, so yes, correct. Okay. FBC is positive, which means it's in tension. Okay. All right, so we're going to go ahead and update our original diagram. Okay, so we go back here. We have our FEC. We have our FBC. Okay, so we have 1096. And we have we're going to go ahead and round up to 775 because it's 0.98, right? So 1096 and 775. The FEC is in compression. Okay, so we're going to go ahead and flip our arrows. And then our FBC is in tension, so it's 775 in tension. Okay, now at this point, we're really only missing one value. Okay, so we're missing the FBE. Okay, so that's going to be our final calculation here. Okay, so it's quite a large one, right? So we're going to go ahead and do E at this point. All right. Okay, so we're doing E. We're solving for FBE. All right, so we got E here. Okay, we know quite a lot about these lines at this point. Okay, we got FBE. We're going to assume it's in tension. We got 500. Whoop. Switching colors on you here. Okay, and we have FEC. Okay, so FEC is going to be 1,096. We have our 500 pounds that's along the y-axis. We have our FBE, which is our unknown. Okay, and we have our FDE, which is 958.33. Okay, so now we're going to go ahead and we're going to set up our we have quite a few angles here. We have our 56.3, we have our 33.69, and we have our 45. Okay, I gotta be honest, I'm a little bit excited about this being our final one. It is quite a long problem. Okay, so if we take these angles, and I probably could have drawn it a little bit larger, right? So really on our unknown angle here, the only ones, or not our unknown angle, but our only ones that are out of kind of out of phase, not along the x or y axis, is we have our FEC is in compression. So FEC is in compression. I drew that the wrong direction. So we have okay, I'm going to look back at FEC here. Okay, so we have our FEC. We're going to have FECX and our FECY. Okay, FECY is going to be going up, FECX is going to be going to the left. Okay, and then for FBE, I'm going to draw it a little bit above. We're going to have FBEX. And then we're going to have FBEY. Okay. I know this gets really confusing, guys. It would be much, much better to draw this with a ruler and draw it larger so that you can see everything and use multiple colors, okay? Just because the diagrams really help you to conceptualize what's happening with the forces. So, okay, so we're going to go ahead and set up our equations, which should be pretty straightforward at this point. So we have summation of forces in the x direction. That's going to be that's going to be FDE. Okay, so that's going to be FDE. Where's my thing? Okay, so we're summing the force in the x direction. So we got FDE. FDE plus FBEX plus FECX, and that's it for the x direction. And then we're summing the forces in the y direction. That's going to be FBEY plus our 500, our negative 500, and then we're going to add to that FECY. Okay, so the x's, we're going to go ahead and start with the, because we know these values, we can start with either one at this point. It doesn't really matter to us. So we're going to start with the y just because that's what we've kind of been doing. It's going to equal 0, right? Okay, so we're going to start off with FBEY, and so that's going to be FBE. Oops, FBE times, so this is opposite over, so it's going to be the sine, right? The sine of 56.3. Okay, plus, so that's our FBEY, right? Plus our negative 500, plus, and then we're going to do FECY, which is going to be, FECY is going to be the, it's going to be positive, right? Yes, it's going to be positive. Okay, and it's going to be 1096, because that's our value for FEC, right? Times the sine of 45 degrees. Is it? Yes, it is. Okay, so it's going to be 1096 times the sine of 45 degrees. Okay, so that's basically it. We aren't going to have to do this other x summation, right? Because when we figure this out, FBE is our last unknown. So this equation is going to give us FBE, which is going to be our final value here. All right, so we're going to go ahead and solve it partially. So we're going to go 1096 times the sine of 45 equals 774.98. Okay, so what we get here, that's a positive, right? Okay, so okay, so we're going to end up with 500 plus negative 774, all divided by sine of 56.3, and that's going to equal FBE. Okay, so let's see how this goes here. Okay, so what we end up with is negative 329. Okay, and that's going to be in tension, so it's pointing down towards the middle of the. It's pointing towards the member, right? The center of the member, so it's going to be in tension. All right, so that is that. So we have FBE is going to be 329.34, and there could be a rounding error in there, and that's going to be in tension.
Like 330.
It is 330.51 precisely. Yes, but my rounding has gotten it a little bit different there. Okay. All right, guys. So that is basically how we do it, and that's going to be it. So really understanding, you know, how these forces are going to be and whether they're in compression or tension is the key thing to solving this stuff. Determining whether, when you come out with an answer that's negative, is that compression or tension. When things flip inside the equation, when you know something goes to compression from tension to compression, knowing that the component vectors flip and understanding that is also key. All right, guys? Okay, thank you so much for your attention.